So let's take a few moments and review pulmonary ventilation and gas exchange. So we know that pulmonary ventilation is the act of breathing. It's inhalation and exhalation. And if we know that, because we've lived with our own bodies, when we breathe, air moves. So what are we up to when we're trying to accomplish this feat? Well, what we're up to is we're using structures and muscles to change volumes of a space. If I can change the volume of the space, I will change the pressure inside that space. And if I can create a pressure gradient, air will move. And air always follows its gradient. Air is always going to go from wherever there's higher pressure to wherever there's low pressure. So in pulmonary ventilation, we're really trying to create pressure gradients, and we're using a space to do that. So that means we have to understand the relationship between the volume or the size of a space and the pressure of the air molecules or gas molecules inside that space. And that relationship's basically our first famous dead guy law. And yes, you need to know the names of the dead guys. So this first law told us that there is indeed a relationship between volume and pressure. And it's because of what pressure is. You know, pressure is basically created when molecules inside a space bounce up against each other and the walls of their space. So let's look at these two spaces here. I have the same number of molecules inside the space, inside each space, and those molecules are hitting each other and then hitting the walls. So in which of these two spaces would the molecules come in contact with the walls more frequently? Well, hopefully you said the smaller space. Given the same number of air molecules inside, in a small space, those molecules will come in contact with the wall far more frequently than they will in a big space. Well, that's what this first famous dead guy law is getting at. And so what we find is that volume and pressure are inversely related. Meaning, if I increase one, I automatically decrease the other, and vice versa. If I decrease volume, I'll automatically increase pressure. So our bodies are manipulating that dead guy law. Our bodies are changing a volume because that affects pressures, which creates a pressure gradient, so air moves. So what are the volumes at work here? Well, one of the volumes is in the pleural cavity. Do you remember where that is? That is actually the space between the layers of the serous membrane, between the visceral and parietal layers. So there's a cavity that's filled with fluid there. And that's our pleural cavity. So that's one volume I can change. The other volume I will automatically change is the cavity inside the alveolus. So there's two volumes here I can affect. The pleural volume is called intrapleural. Okay. And that alveolus one is intrapulmonary. So I'm going to have an intrapulmonary and intrapleural pressure and intrapulmonary and intrapleural volumes. So again, if we look at the moral of the story first, if I increase these volumes, I will cause a drop in the pressure inside those volumes. If I can make this pressure less than the pressure of the atmosphere, the air around me, air moves inside, and vice versa. So let's take a look. This is inspiration. In order to inspire, breathe in. Well, take a breath in. You know that your thorax increases in size. Your rib cage elevates and expands. Well, we're going to use muscles to change the volume of these spaces. So in order to breathe in, I have to contract my diaphragm. What my diaphragm does is kind of weird. When this is your diaphragm, this kind of U-shaped structure there. When your diaphragm is relaxed, it's dome-shaped. And so the volume of this space is smallish. When your diaphragm contracts, it flattens out, and so the volume of this space becomes biggish. So when we breathe in, one of the muscles we have to contract is our diaphragm to make a bigger space. The other thing we do when we breathe in is we contract external intercostal muscles here. So our external intercostals, when they contract, make our rib cage go up and out. So again, when we breathe in, we contract our diaphragm, we contract our external intercostals, and that results in an increase in the volume of your thoracic cavity. Your intrapulmonary and intrapleural cavities get bigger. Well, when you increase the size or volume of these cavities, remember, pressure drops. And so your intrapulmonary and intrapleural pressures go down, and intrapulmonary is the one we're focusing on here. The point at which your intrapulmonary, I'm going to call it IP for now, becomes less than atmospheric, air rushes in, and you've just breathed in. So from the top, when you breathe in, you contract your diaphragm and your external intercostals. That increases the size of the thoracic cavity in the intrapleural volume. That automatically increases the intrapulmonary volume. When you increase the intrapulmonary volume, the pressure, intrapulmonary pressure, drops. And the point at which it becomes below atmospheric, air comes inside the body. Now, quiet expiration is passive. To exhale quietly and calmly, you simply relax the external intercostals and relax the diaphragm. When you do that, the thoracic cavity size decreases. Your rib cage goes down. And remember, your diaphragm goes from being flat to being concave. So between the elastic fibers causing my thorax, my rib cage to kind of recoil, and my flat, doming diaphragm there making this volume smaller, we've accomplished the task of making our thoracic cavity smaller. When we make our thoracic cavity smaller because of all the elastic tissues, we automatically make our intrapulmonary volume smaller. If I decrease intrapulmonary volume, I increase intrapulmonary pressure. And the point at which intrapulmonary pressure becomes greater than the pressure in the atmosphere, air leaves the lungs. Again, that's quiet expiration. So from the top, to exhale, you relax external intercostals and you relax the diaphragm. That decreases the volume of the thoracic cavity, which causes a decrease in intrapulmonary volume. As you decrease intrapulmonary volume, you increase intrapulmonary pressure, and the point at which intrapulmonary pressure becomes greater than the atmosphere, air leaves the body. So that's the story for breathing in and out quietly. If you have to force inhalation or force expiration, you need additional muscles. Because the more muscles you use, the bigger the volume change becomes. And the bigger the volume change becomes, the larger the pressure gradient, and the more air you suck in or push out. So to do forced inhalation and expiration, again, you need extra muscles. Forced expiration is going to utilize internal intercostals and some abdominal muscles. Forced inhalation uses additional muscles as well. So in addition to understanding the process, you should understand how we regulate them, which I'm not going to get into. but I am going to hint at. One of the things that drives changes in your respiratory rate is the amount of carbon dioxide in your blood. And we're going to come back to that in a little bit. But remember, understand this process of breathing in and out, understand the dead guy laws, and understand the actual nervous system structures that set the rate and then modify the rate. All right, so let's take a moment and look at gas exchange. Remember, when we do gas exchange, we're talking about moving oxygen and carbon dioxide. And now we deal with a different set of dead guy laws. One of the famous dead guys told us about partial pressure. So partial pressure. And that famous dead guy said that, finish writing it here, that in a mixture of gases, the amounts of each individual gas added up equals the whole. So I rephrased it and I said something like the whole is equal to the parts. But what that means for us is that whenever you see a percent for a gas, we refer to it as its partial pressure. So if oxygen is 20% in the atmosphere, we would give oxygen a partial pressure of 20. The other thing we know is that these gases have different solubilities. And one of the things that affects that is partial pressure. The higher the partial pressure of the gas, the more soluble it becomes. But we also talked about pH, temperature affecting solubility. One of the things we learned is that while carbon dioxide is highly soluble in blood, oxygen is not. And that's one of the reasons why we have to have hemoglobin, because you can't dissolve enough oxygen in your plasma to meet your needs. So let's look at what drives oxygen. We're going in a moment to look at partial pressure gradients for oxygen. And the partial pressure gradients are what drive movement. So oxygen's always going to go from where the partial pressure is high over to where the partial pressure is low. And that's true for carbon dioxide as well. Wherever the partial pressure of carbon dioxide is high, CO2 is going to move from that area to where the partial pressure is low. Okay, so no worries there. It's just a gas moving with its gradient. In the world of oxygen, we know that if hemoglobin picks up oxygen, not only do we call it oxyhemoglobin, but we call that process oxygen loading. When oxyhemoglobin comes apart, when hemoglobin gets rid of the oxygen, we're going to call that oxygen unloading. Well, how does hemoglobin know when to pick up or load oxygen versus when to unload? Well, the trick for that is yet another famous dead guy. He didn't give us a law, but he did describe how hemoglobin works. And it turns out that hemoglobin's ability to bind oxygen changes with pH. This is the Bohr effect. So in an acidic environment, hemoglobin has a poor affinity for oxygen. Hemoglobin doesn't bind oxygen well when it's acidic. In a neutral environment, hemoglobin loves to bind oxygen. So we're going to see that pH helps hemoglobin know when to pick up or drop off oxygen. In the world of carbon dioxide, we've got options. Some of the carbon dioxide can be bound up to hemoglobin. Some carbon dioxide, because it's so soluble, is simply dissolved in gas form. The rest of CO2 combines with water to make carbonic acid, which pops apart into H plus and HCO3 minus. So we're going to see carbon dioxide traveling in this molecule. So let's put what we know to work. Let's start over here at the alveolus. I said in class, that's not a drop of water, that's an alveolus. In the alveolus, the partial pressure of oxygen is usually high, and that's because you're always inhaling and exhaling. If the partial pressure of oxygen in an alveolus is high because you're always breathing in, that means that the partial pressure of CO2 at the alveolus is low because you're always getting rid of it. If we look at the blood as it comes into a capillary around an alveolus, we see the opposite is true. Just a few heartbeats ago, this blood was in the systemic circulation. So remember, this blood is deoxygenated. The blood coming in here is low in O2, but the partial pressure of CO2 is very, very high. So question number 1, is there a pressure gradient for oxygen? Absolutely. There's a high and there's a low, so the oxygen automatically will diffuse from the alveolus across the respiratory membrane into the plasma, that capillary. I ask, is there a pressure gradient for carbon dioxide? Absolutely. Carbon dioxide will automatically diffuse from the capillary where it's high into the alveolus where it's low across the same respiratory membrane. So the question here becomes, well, what's the fate of these gases? When oxygen enters the blood, it will be attracted chemically to hemoglobin, to that heme inside the hemoglobin. And so we're going to make oxyhemoglobin. Okay. Carbon dioxide here, once it starts to diffuse, some of it will, was just in the plasma, so it just diffuses over. Most of it actually, was bound up in HCO3 minus here. Well, what happens in the blood here, because we're always getting rid of CO2, we drive this chemical reaction this way. So the bicarbonate combines with that H+ and makes carbonic acid, which comes apart into water and carbon dioxide, which diffuses across the respiratory membrane to the alveolus, and we exhale it. So because you're always pulling CO2 out, we drive the reaction in this direction. So that's how we're going to deal with most of the CO2. The last of the CO2 was attached to hemoglobin. And if we think about what's going on here, because this blood has a relatively high CO2, in this location, in this circumstance, and because of the high partial pressure of O2, hemoglobin's story here kind of changes a little bit. At the alveolus, hemoglobin has a high affinity for oxygen. And there's a lot of oxygen here, so we're going to pick up oxygen or load it. Now this blood is going to travel to the tissue. At the tissue, we're going to change story because the gradients are different. This blood coming into the capillary at the tissue has a high partial pressure of oxygen and a low partial pressure of CO2. Just a few heartbeats ago, it was down here at the alveolus doing gas exchange. But the tissue is always the exact opposite. Tissues always use oxygen, which means the amount of oxygen in a tissue is always low. And because they're always making carbon dioxide, the amount of CO2 at the tissue is always high. So what happens here is we're going to change our story. So first, let's look at gradients. Is there a gradient? Absolutely. There's a gradient for CO2 to go from the tissue into the blood. And there's a gradient for oxygen to go from the blood to the tissue. So the gases are all automatically going to diffuse across this membrane here. So the question becomes, how are the gases affected? Well, if we look at CO2, we're going to be adding CO2 to the plasma. Some of it just as dissolved CO2. Some of it stuck on hemoglobin, and the rest of it is going to combine with water to make that acid, which comes apart into hydrogen ions and bicarbonate ions. So most of the CO2 is going to be, again, hidden up in there. Well, if we think about what's happening here, the pH of the blood here is going to be changing. Okay? So, and the pH of this interstitial fluid is changing. So the moral of the story at the tissue is hemoglobin's affinity for oxygen is low at the tissue because this blood's coming into an environment that's acidic. So this ensures at the tissue that hemoglobin unloads its oxygen and then binds the CO2. So again, gas exchange comes down to a couple of main concepts. Is there a gradient? And then the molecules follow the gradient. And then the other trick is, how are we going to carry CO2 versus how do we carry oxygen? CO2 we carry three ways. A small amount on hemoglobin, a bit more dissolved as gas in the plasma or the fluid, and a lot, most, bound up in that bicarbonate. So depending on the partial pressure gradient for CO2, we're either going to pull CO2 into the blood or let CO2 go out of the blood. The story for oxygen is very similar. The partial pressure gradient for oxygen drives its movement, so we either pull O2 into the blood or push O2 out of the blood. And there's only two ways to carry oxygen. A tiny amount dissolved as just a gas, but most of it on hemoglobin. And then the last part is to understand hemoglobin's role. When hemoglobin enters an environment that's acidic, it loses its ability to bind oxygen. Well, what's the environment here that's acidic? The environment, not the blood itself, but the environment. The environment that's acidic is the tissue, is right here, because the tissues are always making CO2. So when hemoglobin enters the blood at a tissue, that change in pH, that acidic environment, causes it to oxygen unload. With hemoglobin at an alveolus, the opposite is true. The blood is acidic, but as it comes to the alveolus is not. And so as the blood enters the alveolus, hemoglobin's affinity for oxygen changes. It now, at the alveolus, becomes high, and we ensure that we oxygen load. So those are the basic concepts. Make sure you have a good understanding of these principles, and you should be able at this point to understand the effects of hypercapnia. If your CO2 levels were high, how would that affect blood pH? And how would your body respond with ventilation? Would you breathe faster or would you be slower? If you need an example of hypercapnia, imagine what happens to you if you have to run across the parking lot. You should also be able to piece out what happens with hypocapnia. You know, if your CO2 levels are too low, how would your blood pH be affected? And how would your body change for pulmonary ventilation? Remember, we use breathing to modify blood pH because it's so convenient to manipulate CO2. So hopefully that helps.